For gases, because there are all these things we need to specify, it's convenient to have what are called standard conditions, sort of a point of reference. So we call this standard temperature and pressure, or we abbreviate that STP. Standard pressure is defined as 1 atmosphere, which is the same as 760 torr. So standard pressure is like normal pressure, right? So that makes that, it's like really easy to establish if you're doing an experiment. Standard temperature is 273 Kelvin or 0 degrees Celsius. That is the freezing point of water. Why did we choose that instead of room temperature? Because freezing point of water is a very easy temperature to establish. If you want the gas in your container at 0 degrees Celsius, you just have to put the container in a big ice bath. Bunch of ice and some water, stick it in there, wait a few minutes. You don't even need a thermometer. You know what the temperature is. So you don't need technology, thermostats, heaters, refrigerators, or anything. So in my mind, that's the reason for these being the standard temperature and pressure. When I don't know the reason for something, because I always want to know why, I make up a reason. It helps me remember. It's like, okay, well, this makes sense because this would be good. So STP is useful when we want to make comparisons between gases. This is hard to compare when all these different things are different. So that's STP. Molar volume. We've talked about molar mass, right? Molar mass is the mass of 1 mole of substance. Molar volume is the volume of 1 mole. This refers to a gas at STP. So the volume of 1 mole of gas at STP. So at STP, the temperature is 273 Kelvin. The pressure is 1 atmosphere. Let's calculate what that would be. 1 mole of gas tells us that that's N equals 1 mole, right? We're calculating the mass of exactly 1 mole, and we can assume that these are also exact numbers because they're defined. So if we want to calculate volume, we just did one of those, right? So volume equals nRT over P. That's just a rearrangement of the ideal gas law. And we can plug our numbers in. N is 1 mole. R is 0.08206 liter atmospheres per mole Kelvin. Temperature, 273 Kelvin. Pressure, 1 atmosphere. I know what the number is, but I'm going to calculate it anyway. .40 liters. This is one place where I'm just not really keen on using the 273. I think 273.15 would be better. So I'm going to do that again. If you use that, you get to 22.41 liters. Not a huge difference, right? This is a very useful number. Not sure why, but they usually round that to 2 to 3 sig figs. 22.4 liters per 1 mole of gas. And that's at STP. 1 mole of nitrogen? 1 mole of hydrogen? Does it matter? No, it doesn't. Why doesn't it matter which gas we're talking about? It's the 1 mole is a specific number of particles, right? Why doesn't it matter how big the particles are? Well, they do make up one unit, but how much space is between them?
Well, this is where you said it doesn't matter the size because
Right.
how the students are in the big classroom.
Yeah, so this is where, did I talk about Wyoming and an elevator and football players?
You talked about kindergartners.
I talked, yeah, that kindergartners was a different part of it. Okay, so I did talk about Wyoming. Population's the same as Fresno, right? But it's in this huge area. So the size of the people doesn't matter. When you get people closer together, like in an elevator, a small elevator, then the size of the people matters a lot, right? This is a gas. This is Wyoming, not an elevator. And so there's so much space between the particles that it doesn't matter if they're really big particles or really small particles. Yeah, there's a lemur on the pole. He was in the cupboard last week, now he's on the pole. He is cute. And that's not distracting at all, is it? That's okay. I keep looking at it because I look at the clock and there's the lemur. That's Mr. Yates's bit of humor. Okay, so back on task here. So the molar volume of any gas at STP is 22.4 liters per mole. This is a very useful conversion factor. If we know the volume of a gas at STP, we can know how many moles are in it. You don't have to weigh it. You don't have to react it to find out how much of stuff it reacted with. You can measure the number of moles by measuring the volume at standard temperature and pressure. It is important, though, to realize that the mass of that 1 mole of gas would be different. Same number of particles occupying the same amount of space, but one's going to weigh more than the other. That's going to be different depending on the gas. So here we have a picture. 3 balloons. This one's filled with helium, neon, and methane. All 22.4 liters. At STP, we know that there's 1 mole of gas in each. 6.022 times 10 to the 23rd atoms of helium. Same number atoms of xenon, same number molecules of methane. But how much is this balloon going to weigh? 1 mole of helium. No, I'm asking you for a number. How much? 4.003 grams. How did you do that? It's the mass of 1 mole of helium. Periodic table, yeah. How about the xenon balloon? 131.3 grams. Because this is the molar mass of xenon. Xenon particles are much bigger and much heavier. Okay, so the mass of these samples of gas will be different, but the volume occupied by the same number of particles is the same. This is a weird thing about gases. Liquids and solids don't do that. We could calculate the molar mass of methane, but I don't feel like it. Any questions? A xenon balloon would not float, it would sink. And it would sink pretty quickly, because that's a lot more dense than air. If we think about densities, each of these gas samples occupies the same volume, so you can calculate the density. The density is the mass divided by the volume. So for helium, it would be 4 grams per liter, and for the xenon, it would be 131.3 grams per liter. So a lot more dense. Yeah. Xenon balloon is not going to be much fun. So density, as I just mentioned, density is the ratio of mass to volume. And we've done density things before, mostly with liquids and solids. For liquids and solids, we typically used grams per milliliter or grams per cubic centimeter, because that's a convenient unit. Gases are much less dense, and so the units are usually grams per liter, because that gives us more reasonable numbers. So we're often either given a gas density or we have to calculate a gas density, And one of the ways you can do this is, say, well, 1 mole is going to have the mass equal to the molar mass for that, right? The mass of 1 mole is the molar mass. We know how to calculate that. At STP, the volume of 1 mole of gas is always going to be 22.4 liters. So at STP, we can calculate the density of a gas very easily by taking the density here. I screwed up over here. I was dividing by 1 liter. Divide by the volume, 22.4 liters. I don't know where my brain was. It took a coffee break, and I don't even drink coffee. That's really weird. Now I'm lost. And Dilseri disconnected. Okay, so we can calculate the density of gases at STP, so the density of helium. The molar mass, the mass of 1 mole, would be 4 grams, and the volume of 1 mole is 22.4 liters, and so we can find that the density would be 0.179 grams per liter. For nitrogen, 1 mole of nitrogen weighs 28.02 grams. 1 mole of nitrogen occupies a volume of 22.4 liters at STP, and so the density of nitrogen would be 1.25 grams per liter. Those densities, though, will change with temperature and pressure because gases expand and contract. So those are the densities at STP. The density is proportional to the molar mass. And so your book goes through this and gives us this equation. The density equals the pressure times the molar mass divided by R times T. If you remember that and want to use this, that's fine. Personally, I don't like this. It's another equation to remember, and it's just so completely not necessary. I think it's better if you have to calculate a density, like I think here's a problem we have to calculate. Calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees Celsius. So you could use that equation, but then you have to remember the equation. So I look at a problem like this and I said, well, calculate the density. Okay, I've already learned the density equation, right? Density equals mass divided by volume. So I need the mass of this gas and I need its volume, but they don't tell me how much gas. So what I'm going to do is I'm going to choose 1 mole of gas because it makes the calculations easier. Now I can calculate the mass, I can calculate the volume. Calculating the mass is actually pretty easy because it's just the molar mass. What's the mass of 1 mole of xenon? 131.3 grams. That's on the periodic table, right? The molar mass. I need to divide by the volume. How do I find the volume? Ideal gas law. B equals nRT over P, a rearrangement of the ideal gas equation. So I'm using 2 equations that I had to use anyway, had to know anyway. So we chose 1 mole, so N is 1, exactly, because we picked it. R is always the same thing. Liters times atmospheres, divided by moles times Kelvin. Temperature. Okay, they gave me the temperature in Celsius. Of course they did. I've actually never seen a thermometer that was calibrated in kelvins. It's always calibrated in Celsius. So we have to convert that to kelvins. Oh, I better not do that in my head. If I can't remember what story I'm telling, then I should not do math in my head. 319. No. See, I can't even do it on the calculator. 318 Kelvin. I have to put the temperature in kelvins. So there's my temperature, 318 Kelvin. All of that divided by the pressure. Oh, they weren't nice to us on that either. 742 millimeters of mercury. I need this in atmospheres because that's the unit in the ideal gas constant. 1 atmosphere is exactly equal to 760 millimeters of mercury. So I got 742 divided by 760. 0.976, 3 sig figs, 31 atmospheres. Zero 0.97631 atmospheres. Check the units: atmospheres, atmospheres, moles, moles, kelvins, kelvins. 0.08206 times 318 divided by 0.97631 equals 26.728. That's the volume. So I'm going to put that volume up here, 26.728 liters. Density is mass over volume. 131.3 divided by 26.728 equals. That's going to have 3 significant figures because the volume came from a calculation in which we had a pressure and a temperature with 3 sig figs. So we're going to say that this is 4.91. The unit there would be grams per liter. Okay? You can use the equation if you want to, but this is easier for me to remember because when I'm in a stressful situation like an exam, I tend to forget equations, right? So that density equation, we don't use that one very much. This one back here, this guy, we don't use that very much. And so it's easy to forget that. I prefer to take the 2 things and put them together. Any questions? One of the cool things about gases is that you can figure out what their molar masses are without using high-tech equipment like a mass spectrometer. So the molar mass of a gas is easier to determine because you can figure out how many moles of gas you have by measuring the pressure, the temperature, and the volume of the gas. So you can do, and we're going to do this in lab, I think it's next week, experiment 5A. A volatile liquid is a liquid that will evaporate easily. So you can take a volatile liquid, put it in a container which you know the volume of, you heat it up and causing it to expand and form a gas, and you allow the extra stuff to come out so that you have the same pressure inside the flask as outside the flask. You know the volume, the temperature, the pressure. You can calculate the moles of gas. Then you condense that liquid back down and you weigh it and you find out the mass of it. The molar mass of that substance is going to equal the mass divided by the number of moles. It's pretty neat. So here's an example problem. A sample of gas has a mass of 827 milligrams. Its volume is 0.270 liters at a temperature of 88 degrees Celsius and a pressure of 975 millimeters of mercury. Find its molar mass. So the question here is, what's the molar mass? So I'm going to ask myself, well, what is molar mass in general? I usually abbreviate it with a capital M. It's not the molarity M, it's this other M. Let's call it MM, molar mass. That is grams divided by moles, right? It's the mass of 1 mole of substance. So, do we know the mass of this gas sample? We do. It's this many milligrams. So, what do I need the unit to be, though? Grams. Well, this is 827 milligrams. Instead of writing milli, I could write times 10 to the minus 3 grams. This is not correct scientific notation, but the calculator's going to understand it, and it's going to work in the calculator just fine. Or you can actually do the whole thing, and it'd be 0.827 grams. Divide by the number of moles. How do I find the moles of gas? What equation do I need? The ideal gas law. PV equals nRT. Now I want to find N. N equals PV over RT. So I need the pressure of the gas. Well, darn, there it is in millimeters of mercury again. So we got to convert that. Let's do that down here. 975 millimeters of mercury, converting that to atmospheres, divided by 760 millimeters of mercury. We use this one, oops, don't cross off the 760. We use that one a lot. 975, turn on the calculator. 975 divided by 760. 1.2828 atmospheres. So that's the pressure. Stick that in here. 1.2828 atmospheres. And then I need the volume. Here's the volume. Thankfully, they gave that to us in liters. We don't have to convert that. Volume in liters. I'm going to divide by R, 0.08206. Liters, atmospheres per mole, Kelvin. And the temperature, 88 degrees Celsius. Convert that. $361. This calculation can be dangerous when you put it into your calculator. It's the numerator, 1.2828 times 0.270 divided by 0.02008, that number, and then divided by 361. If you really, really want to multiply these, you need to put parentheses around the whole thing in the denominator. Otherwise, you're going to end up with a very different answer. So make sure that you get the same answer here. 1.2828 times 0.27 divided by 0.08206 divided by 361. 0.011691 moles. If you got a really big number, it's because you miscommunicated with your calculator, and instead of dividing by 361, you multiply by 361, which makes you off like super much. So that's the number of moles. So I need grams per mole, so I'm going to plug that in over here, 11691 moles. So 827 EE minus 3 divided by 0.001691 equals 489. Nope. I divided by 0.00169. That's not good. 489 would be a really high molar mass for a volatile liquid. So I'm going to do my math again. That's better, 70.738. 3 sig figs, units are grams per mole. So the molar mass is 70.7 grams per mole.
What's the big M in the density equation, molar mass?
In the density equation, yeah, that funny one?
Yeah.
Yeah, let's go back and look at that. This one.
Yeah.
This weird looking M, that's like an italics, capital M. There's way too many M's, aren't there? This isn't molarity, that's molar mass. Because that's not confusing at all, right? So this script, capital M, is molar mass. And just a regular capital M is molarity, right? And then we have a lowercase m, and that is meters. And then MOL is moles. And, you know, it's just, yeah.
So if it's fancy, it's molar?
If it's fancy, it's molar mass. I avoid using an abbreviation for molar mass. I know, handwriting, it's really tough to tell which one you mean. So capital M is a little bit better, but maybe just the words molar mass would be the best. Did you have a question?
Yeah, and the problem you just finished, the one before that one, you know how you put M over V? That V was in milliliters, right? You converted it to milliliters?
The volume was in liters. So for gases, we typically have volume in liters because that gives reasonable volume, reasonable densities.
So straight gases, it's liters, but everything else in milliliters?
Yeah. Yep. Any other questions? Okay, we did that one. Okay, so here is an example like you might get, data from an experiment. And we're going to do this experiment, so, maybe pay attention to this. An organic chemist isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask and puts the flask in boiling water, which vaporizes the liquid and fills the flask with gas. She closes the flask and reweighs it. Her data is given below. Calculate the molar mass of the liquid. So we've got all this stuff. When you actually do the experiment, you get more stuff because you can't just flat out weigh the gas or weigh the liquid. There has to be a container. So we've got the mass of the flask. We've got the mass of the flask with the gas in it. So a common thing that I see happening in lab is that students use the mass of the flask with the gas in it. Okay, the glass flask has nothing to do with the molar mass of the liquid or the density or whatever we're trying to calculate. It's just the container. Okay? If you're trying to calculate the mass of your puppy so you can give him the right amount of medicine, we talked about you get on the scale by yourself, you see how much you weigh, you get on with your puppy. You're not going to use the mass of you and your puppy together to figure out how much medicine. You're going to kill the poor thing, give it way too much medicine, right? We don't want the mass of the flask in here. We want the mass of the gas. And I think there's something about walking into a chemistry lab that makes some students just lose all shreds of common sense, right? They're just everything's out the window and they're like, I don't know my name, right? You just some very, very simple things you suddenly can't do, right? And it doesn't mean that you're stupid. It's just this thing that happens to us, right? I can't remember my children's names, and I gave them their names. I started calling them K1, K2, and K3. Because people at school can't remember their names either. Oh, there's K6. I have 6 kids. Yes, and they are all mine. So here, the mass of the flask with the gas and the mass of the flask. We don't care about the flask. If we look at the words here, this is a big clue what we need to do. If we want just the gas by itself, we need to get rid of flask, right? So we need to subtract. So we're going to take, to find the mass of the gas, let's choose a pen first. The mass of the gas is going to be the 78.416 grams minus 77.834 grams. And, you know, I see students write this out and do it longhand on the paper. I'm not impressed by your ability to do subtraction longhand, especially when you screw up and you get the wrong answer. It happens more often than you realize. Use your calculator. It's 0.582. Because, you know, we have, my husband calls them brain farts, right? You're going along and you know what you're doing, but it's like when I say 2 and write 4. I mean, how does this happen? We do that, stuff like that all the time. So we got the mass of the gas, and then we're like, oh, now what are we trying to do again? We're trying to calculate the molar mass of this thing, this liquid. So then I ask myself, well, what is molar mass? Let's avoid all the confusing symbolism and say molar mass. It's not that many letters. The molar mass equals grams divided by moles. So I need the mass in grams, and I need to divide by the number of moles. Well, I just figured out the mass of it, right? So I can plug that in, 0.582 grams. I need to find the moles. I have all the information I need here. I have the volume, the temperature, and the pressure. Ideal gas law will allow me to calculate N. N equals PV over RT. Just a rearrangement of PV equals nRT. So I'm going to start out and, well, none of these units are right, are they? The ideal gas constant has liters, atmospheres, and Kelvin. And so we have to get volume, temperature, and pressure into those units. So this milliliters, 0.213, very good. So converting from milliliters to liters involves moving the decimal point 3 places. We just need to make sure we're going the right direction. Milliliter is a small unit. It's got the big number. Liter is a larger unit, so we need to move it to make the number smaller. Or write out the whole thing. Temperature, 100.0 degrees Celsius. Because of this 0.0, I'm going to use the 273.15. And that's going to be 373.15 with the last significant figure in that first decimal place. And then the torr, remember torr and millimeters of mercury are the same thing. So 1 atmosphere is 760 torr. So 0.99210 atmospheres. Again, don't round those numbers off yet. I mean, this one came out to the same number because that's what happens when you convert in the metric system. But these, we're going to get differing numbers. So don't just round that off. Keep the extra 2 digits. Now I can plug these numbers in. 0.99210 atmospheres times the volume, 0.213 liters, times divided by the ideal gas constant, 0.08206 liter atmospheres per mole Kelvin. And the temperature, 373.15 Kelvin. 0.99210 times 0.213 divided by 0.08206 divided by 373.15 equals. This is a small number. That's okay. This was a small flask. Those leading zeros are not significant figures. I want to keep 3 sig figs, 690, and 2 extras, 1, and that's my number of moles. 1 mole occupies 22.4 liters at SCP. This is a lot smaller than that, so we should expect our moles to be a lot smaller than 1. So there's my number of moles. I can plug that into this equation up here, 0.0690011 moles. And you can have that in scientific notation, that's fine. 0.582 divided by 0.0069011 equals 84.334, 84.3 grams per mole. Any question? Is that a reasonable molar mass? How do we know? Give me an example of an unreasonable molar mass. A negative one. That's unreasonable. How about 0.002 grams per mole? Could anything have that molar mass? No. What's the smallest molar mass possible? 1.008. Very good. If you had atomic hydrogen, it would be 1.008 grams per mole. You can't have anything smaller because that's the smallest atom. And that doesn't hang out by itself. It's usually in a molecule, so it's 2.016 grams per mole. If you have a really, really big number, like 5,000 or 8 million, now you can have molar masses that are that high, but they're not going to be volatile. Okay, volatile liquids are going to have molar masses that are, probably 100 grams per mole or less.